Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. A bit about the show you're about to hear. This show is part of a series that I'm really excited about, in part because I've been working to bring it to you for quite a while now. The focus of this series is a sampling of the really interesting work being done over at OpenAI, the independent AI research lab founded by Elon Musk, Sam Altman, and others. A few quick announcements before we dive into the show. In a few weeks, we'll be holding our last TWIML online meetup of the year. On Wednesday, December 13th, please join us and bring your thoughts on the top machine learning and AI stories of 2017 for our discussion segment. For our main presentation, formal TWIML Talk guest Bruno Gonçalves will be discussing the paper Understanding Deep Learning Requires Rethinking Generalization by Shiyuan Zhang from MIT and Google Brain and others. You can find more details and register at twimlai.com/meetup. Also, we need to build out our 2018 presentation schedule for the meetup. So if you'd like to present your own work or your favorite third-party paper, please reach out to us via email at team@twimlai.com or ping us on social media and let us know. If you receive my newsletter, you already know this, but TWIML is growing and we're looking for an energetic and passionate community manager to help manage and grow programs like the podcast and meetup and some other exciting things we've got in store for 2018. This is a full-time role that can be done remotely. If you're interested in learning more, reach out to me for additional details. I should mention that if you don't already get my newsletter, you are really missing out, and you should visit twimlai.com/newsletter to sign up. In this show, I'm joined by Jonas Schneider, Robotics Technical Team Lead at OpenAI. While in San Francisco a few months ago, I sat down with Jonas at the OpenAI office, during which we covered a lot of really interesting ground, including not just OpenAI's work in robotics, but also OpenAI Gym, which was the first project he worked on at OpenAI, as well as how they approach setting up the infrastructure for their experimental work, including how they've set up a robots as a service environment for their researchers, and how they use the open source Kubernetes project to manage their compute environment. Check it out and let us know what you think. I really enjoyed this one. A quick note before we jump in. Support for this OpenAI series is brought to you by our friends at NVIDIA, a company which is also a supporter of OpenAI itself. If you're listening to this podcast, you already know about NVIDIA and all the great things they're doing to support advancements in AI research and practice. What you may not know is that the company has a significant presence at the NIPS conference going on next week in Long Beach, California, including 4 accepted papers. To learn more about the NVIDIA presence at NIPS, head on over to twimlai.com/NVIDIA and be sure to visit them at the conference. Of course, I'll be at NIPS as well, and I'd love to meet you if you'll be there, so please reach out if you will. And now, on to the show. All right, well, hey everyone, I am here at the OpenAI offices, and I am with Jonas Schneider. Jonas is a member of technical staff here, as well as being the technical team lead for robotics. Welcome to the podcast, Jonas.
Hey, glad to be here.
It's great to have you on the show. Why don't we get started by having you tell us a little bit about your background and how you got interested in artificial intelligence?
Yeah, so my background is actually, I work on OpenAI's robotics team, but my background is actually in software engineering.
Okay.
My background is neither in robotics, like classical, like academic robotics, nor machine learning, which is, of course, like OpenAI's big focus.
Right.
And so in the robotics team, we kind of have a couple of different skill sets coming together. There's roboticists, there's, of course, machine learning experts, and also software engineering people like me. So before OpenAI, I was actually a software engineering intern at Stripe. That's also where I met our CTO, Greg Brockman, who's now CTO at OpenAI. And so basically, yeah, and so that was actually like while I was still in college. And so after I was done with college, I actually reached out to Greg and was like, so what's up these days? What kind of stuff are you working on? And so he introduced me to OpenAI.
Fantastic.
Yeah, and so I actually got started working on OpenAI Gym. So that was kind of like I was a contractor for OpenAI there, basically working with Greg. And so that's how I kind of got started thinking about all these AI, ML things. And then eventually I got started working on OpenAI's robotics team.
Awesome. So tell me a little bit about the work that you do on the robotics team.
Yeah. So the goal of the robotics team basically is to enable new capabilities for robots. So today's robots, they're really good at like very specific tasks. For example, like in a factory robot, you have an assembly line and you have a robot that can place one very specific screw into one specific location on the part that you're assembling, for example. And robots are great at that. They're really good at that. They have very, very high precision. They can repeat this movement like tens of thousands of times, and they never get tired or anything. But the issue is that these environments are very constrained, of course, because like that's how a factory is. Like everything is super precise. Whenever something like unexpected happens, you just abort, basically. And and then the human goes in there and like figures it out and like resets, and then it goes on again. But so that's very different from, for example, like a home environment where like if you're trying to clean up someone's apartment, for example, where like unexpected stuff happens all the time and you're like something like falls over and then you have to like react to that and pick it back up, for example. So this is like a very simple task, but it turns out that like today's robots are actually not that great at operating these unconstrained environments. And usually the reason for that is that they are pre-programmed, basically. So when you have this factory setting, someone, like when you set up the robot initially, someone goes in there and basically like programs this exact movement pattern for the robot. But of course, and that works great in this constrained environment, but in the unconstrained environment, you actually can't really do that because you have to react to what's happening in the environment. And so that's why today's robots are pretty restricted in these kinds of environments, and we're trying to and working on solving that.
Nice. So it sounds like we're talking about the environments as being constrained and unconstrained, but in a lot of cases, it's my sense that the constraints themselves are artificially imposed. Like the factory environment is constrained because it has to be, because that's the way they can get the robots to work. Like, do you look at applying this stuff in the industrial settings as well?
Well, so the thing is, like, you're of course exactly right that basically today's automation, like basically everything, like the way these factories are designed is exactly so that the robots can function. I think for the most part, it will be, or at least with the current state of like capabilities of ML-based systems, it will actually be pretty hard to be better than this constrained environment if basically your application or your business is like fine with operating in a constrained environment. So for example, like while it might be nice to, let's say there's a Tesla like robot that moves the auto bodies around. And then let's say like of course it would be nice, for example, like if it would be smart enough to react to if it like dropped the thing on the floor, if it could like pick it back up and just like continue going on. But these events are so rare that and basically of course there's like a lot of other just engineering factors there where like you got to be sure that if the robot is in this like reaction mode that it doesn't accidentally like cause like more failures somewhere else in the system. And basically just because these events are so rare if your environment is already constrained. So we're not really looking at that, I guess, like definitely in the short or medium term.
I'm thinking about applications like Pickandplace types of applications where I've seen a number of research that's kind of in the context of, today, a robot that's being used to bolt stuff in, right? It's getting these bolts that are like preloaded into, a very constrained, like a harness that basically it can bolt in, right? But some of the examples show that in some instances, you might want to just put a box of bolts and let the robot kind of grasp the bolts and then from there bolt them in. And I guess the question is, have you looked at is that really practical? Like, is that where you see the application of this kind of stuff? Or it's like, no, the industrial environments, we've got that kind of figured out. People probably aren't going to, switch from using these, the very rigid environments to the more unstructured environments to save a little bit of that upfront cost.
Yeah, so I think there are definitely some opportunities, basically, specifically in the areas you mentioned, like machine tending, basically, where like you have this inbound like box of parts, and they come from some vendor, and you basically have to like feed them to the machines correctly and like unpack them. And that is again because it's kind of an unconstrained environment. You don't really know, like they might change like their shipping material, and suddenly it looks different, and you have to process this package differently. And also one other kind of interesting example is actually plugging in cables. So that's something that all these industrial robots are also very bad at, it turns out, because like cables are deformable. And basically there again, you might have to react, like if the cable is bending weirdly, you have to like poke it so it falls into the correct place. And so this is actually something that consumes a lot of time in, for example, like auto assembly, where basically you can do the entire frame. It's all roboticized and all super nice. And then you have a bunch of people like installing all the stuff in the interior, for example. And that includes actually it's like one very specific task that people have tried to automate using like classical robotics. It's plugging in these like connectors, basically. Yeah. Or I guess maybe like a day-to-day variant of this would be like plugging in a charger into like plugging your phone into like a phone charger. Right. But it turns out basically for these problems, you actually like these are surprisingly hard.
Yeah.
Because you have to like figure out the like exact positioning for the charger and then plug it in correctly.
So we built USB-C and like Lightning, the reversible ones, to make it easier for the robots to charge our phones for us.
Yeah, so I think definitely like for the industrial applications, like while it might be hard to basically in the short term improve on the stuff that is already handled by robots, there are definitely a lot of fringe cases that like there's no way that you could currently even like get close to automating it, and new technologies could enable that.
Okay. So tell me a little bit about some of the areas of research that you're pursuing to kind of enable this vision.
Yeah. So basically the thing we're very interested in is basically acting on and reacting on feedback from the real world. So basically this kind of feedback is really also what gives humans this super good like manipulation and like super good like robotic skills, basically.
Okay.
So one quick experiment you can do to verify that is if you try if you put both of your index fingers out like horizontally.
I'm doing this now.
Yeah. Okay. And you try to move them together and like touch the fingertips. And it's very easy to do, and you can always do it. Sure. Yeah, but now try doing it again with your eyes closed. Mm-hmm. And it turns out this is actually really hard. Huh? Yeah, like after a while you can like if you have like the touch feedback. Yeah. But basically, so the thing there is that like actually human motion is not very precise, but it is very good at like figuring out, oh, I'm like off in some direction,
so
and then correcting for it.
Fine-grained feedback and correction.
Exactly. Yeah. And so that is actually a thing that again, these like industrial robots, like they don't really do that on like a higher level. They do it on like a very low level of like, am I in the right place? But this gets harder if you have like other objects or something that you're interacting with. And so this is one area that our research focuses on, basically taking data from the real world and using that like online in the loop to have the robot be able to like react to what it's doing and what like the things it's interacting with, which could be like a block or like whatever object that you're working with is doing. And like if you're like grasping it correctly, for example, or if you're moving it to the right place.
And so how do you do that?
Yeah, that's a very good question. So there we're building on the large body of work that has been done in the computer, like in the like ML based computer vision areas. So basically we take a convolutional neural network that's been trained on ImageNet to do this like image recognition challenge. Okay. And then we basically slice off the last layers of that network where it does this thing of like classifying an object into categories.
Learning.
Yeah. And so basically the parts we want from that is basically the lower level features of the network, like figuring out like where edges are, where like these like small features are. And then we instead train it to predict the state of the world, basically. So we're using this machine learning pipeline basically to feed it an image from like a normal webcam or something like that that's attached to the robot. And then have this neural network that uses this image to predict like where am I and what state am I in? Where's the object that I'm interacting with? And then we use that to correct the movement of the robot.
Are we close to doing this? It seems like it would be helpful to do this in 3 dimensions. Like, are we close to that at all? Or
I think so. So maybe not for the general case, but probably if you have like basically something where you know at least a little about like what kinds of objects you're dealing with, then I don't think anyone has done it yet, but it's like we think it would probably be doable. So the work that we've done, we use this technique called domain randomization, where we basically so questions, of course, how do you train this network? So what I just mentioned earlier with like predicting the position of things, and the way we do it is basically we create chaos in simulation. Because the problem is, if you just feed it images from a simulator, the real world will look different, and then it will just get confused and be like, "This is weird. Why is there like a pixel in the back that is now like bright where it was like dark always before?" And the way we get around that is by basically randomizing everything in the simulator. It looks pretty crazy because we basically replace all the textures in this like 3D rendered scene with random textures, like random colors, random patterns. We used to call it the disco. because it's just random colors everywhere. And basically this kind of makes the network robust against like variations in the environment. And so this is actually, and basically you can measure that like if you do this, then the real world will look as just like another incarnation of this random setting, and it will work. And if you don't, it will just be like completely off, basically.
Okay. Yeah, one of the projects that Peter Beals is working on is like tying a knot, using a robot to tie a knot in some string. And he's got an interesting video about this, but one of the comments in the video or the commentary on the page is like, it works great if the rope is on a green table, but it totally fails if the rope is on a red table or if the rope is like striped or something like that. It sounds like this domain randomization is, trying to solve for that same kind of problem. Right?
Yep. Yeah, totally. I think so for the like rope, like for the basically rope stuff specifically. Yeah. So the reason why people do this at all is because a rope, like similar to the phone charger or like the phone connector, right, is that because a rope is flexible. Like there's not like just like a block or something. And basically to tie a rope, you have to like either you have to have some internal model of like how is it going to bend if I turn it this way. So I guess people just like work on this in like a decoupled way, like decoupled from the like perception way. But this seems very plausible for if you like put these two results together to create something that can tie knots in arbitrary colored environments.
Yeah. Now the other thing that it makes me think of is Apple's recent CVPR paper where they used GAN approach to take simulated images like from a video game engine and kind of make them look like real images so that they would perform better in the real world. Like, your ultimate goal is to have this robot perform well in the real world. You are trying to avoid overfitting by kind of doing, randomization of your backgrounds and, funky colors and all that kind of stuff. But do you still then have the problem of, hey, this doesn't look like the real world? And like, how do you approach that?
This is actually very interesting, like high-level questions that I don't think there's a definitive answer to. It's basically the question of like, should you invest time in making your simulations like super nice and photorealistic, basically, to have like special rendering artifacts of like light reflections and basically just make your environment, make your simulation be almost indistinguishable from the real world, or whether you can actually get away with having really lacking simulation, basically, that is like very rudimentary, just has like geometry and like edges and a couple of like 3D lights. And then you can use like neural network regularization techniques to basically use that to make the network robust against it.
And more generally, in the case of your research, using the domain randomization, like what kind of performance have you seen in the real world? And have you explored ways to enhance real world performance beyond the domain? Are there specifics to the simulation environment that cause your training to kind of overfit on simulated looking images?
Yeah. So I remember that when we were initially doing this domain randomization work, so the setting that we did there was we basically had a table of like different colored like wooden blocks. And then we had the robot, basically you could give it commands of something like stack the green block on top of the blue block. And then it would like basically correctly localize these blocks. And this was with an accuracy of, I believe, a couple of millimeters. So it was pretty decent for like, given that this was really like just a normal like HD webcam, and like basically nothing that's like super specialized robotics equipment. But I actually remember that initially, sometimes it was just failing randomly and we didn't really know why.
Okay.
And then it turned out that if there was someone standing in the background, then
like casting a shadow or something like that.
Exactly, or just having like a leg or like a foot in the image that threw it off. And that is actually basically like these kind of things encourage us to just make the simulation crazier, basically. Yeah. And then if you have these random distractors appear in the background during the training as well, then it will actually be again robust to that.
And so how did you characterize the performance gains, after using the domain randomization?
The way we measured it actually is we just had like an actual like object tracking system and just measured the error from that. But of course, it's also just reflected in the like success rate of like how often could you like stack the correct block like on top of the other one. And basically, if it didn't do the domain randomization, it would just like run into the table or something. Okay. So it was like very, very, very off. And basically,
so your performance metric was bad versus good.
Yeah, sort of. Yeah,
That's fair enough.
Yeah, so like basically what we did initially when we're doing the domain randomization is we actually, one of our researchers, Josh, spent a very long time basically just moving around pieces in the real world and like adjusting the like camera position and basically just fine tuning it so it would be like just right. And then it would like appear to work, but then as soon as you basically like you could see that it wasn't really working. Like it was only working if you like basically like manually overfit it to like one very specific instance. But basically the domain randomization helped with that.
Okay. And so did you build a custom simulator to do this, or did you use some off-the-shelf thing?
Yeah, so pretty much all of what we do these days is running in Motoko.
Okay, Motoko?
Yeah. So
tell me about that.
Yeah, so Motoko is this physics simulator developed by University of Washington professor Emma Todorov.
Okay.
And it's pretty much the standard in basically these like kind of like robotics and like robotics related tasks. It's also used for all the physics related environments in OpenAI Gym. And so basically, if you've ever seen the like yellow like humanoid walking around, that's Motoko. Okay. And basically having these like capsule geometries. And the good thing about Motoko, as opposed to like, of course there are many other physics engines, like game physics engines. There's NVIDIA Physics.
Right.
There's a bunch of it's like from like Unreal Engine. They all bring their own.
NVIDIA announced some new simulation engine at the last GTC. I forget. Da Vinci or some kind of name thing. Flex? I don't. I thought it was a person's name.
NVIDIA has a whole bunch of them because they really like making beautiful things. So the thing that game engines do for the most part is they are often not super concerned about accuracy or physical realism, which is totally fine. They're just working on making something that looks great and is performant too. And Motoko kind of comes from a different perspective there, where it comes from like robotics people, basically. And they are using this for like optimal control, which is kind of the analytical way of like how do you control a system to achieve a given task. Mm-hmm. And it has pretty good features for accurately describing an actual physical robot. Like it can do things like friction and like tendon based, so like where you pull on cables to move the robot around.
Okay.
It has a bunch of these things that like you could implement them like on top of the game engines for the most part, but they just don't come with it. And also Motoko is just like engineering wise, it's pretty practical. It's just like a library that you link against and then you can just use it.
Link against, so it's like C++ or something?
Yeah, exactly. Okay. Yeah, so like it's not open source, it's commercial, unfortunately. So
it seems like a lot of the popular simulators are like, is there a dominant open source simulator?
Yeah, there's Bullet. I think Bullet is pretty popular, and we've actually been looking at it, like maybe switching to that, just because it's
open source.
That's pretty much it. Because it's just like on like a day to day, it's just very convenient to be like, what is happening? This is weird. Let me just dive into the code and see what's going on.
But also, I would think to make it easier for other people to replicate your results and to, try to build on the kinds of things that you're doing. For sure. You don't have to say, well, you have to first go get a license. And
so I believe they do have like pretty favorable agreements, at least for students. So I think as a student, you can get it for free.
Okay.
But so like the good thing about Motoko is basically that it's like, while it's kind of like a walled garden, it's a pretty nice walled garden, and and things
said every walled garden maker.
Well, we're not garden makers. So.
No, I'm putting the words in Motoroko's mouth.
That's true. That's true. The one thing where we've actually been eyeing some of the game engine physics simulators as well is actually exactly like dealing with these deformable objects like the cable or the rope or liquids, even like stuff like that. That is something that Motoko can't really deal with because it's entirely like a rigid body simulator, and it basically like its performance scales with the basically like it gets slow very quickly if you have a bunch of things like moving around.
Okay.
Basically, like of course the scale of things doesn't matter at all because it's just like meshes, it's just numbers. But if you have like let's say if you had like a bowl full of like 1,000 pearls or something, it would be pretty gnarly in Motoko probably. We haven't tried it, but we have tried like, I believe we've basically tried to do like a Jenga, kind of like a Jenga like setup, and it would just like jiggle around and then eventually like kind of explode or just fall apart. So I think there's like a limit of like maybe like a couple hundred of rigid individual bodies flying around. Or not flying around, but moving around.
Is that rigid body simulation something that lends itself to distributed compute, or does that not work so well? Or does it just Motoko not support that?
That's a good question. So I think I believe I believe the creators of Motoko have tried to basically run it under OpenCL, so to like a GPU accelerated. Mm-hmm. But I think the main problem with that is it's very similar from the computation you would run for running a neural network, where it's basically just like a bunch of like matrix multipliers or like related things. But for the physics simulation, you actually have a lot of branching, because you run like a collision detection system, and then you do something that's like, if there's a collision, then do these things. Mm-hmm. And you do that for like all the collisions in the scene or something like that. Okay. And that is something that like, at least like today's GPUs, I can't deal super well with that. Okay. So I think actually this was like a long time ago, but I think NVIDIA, they used to sell something like a physics processing unit, a PPU. Actually, I'm not sure if it was NVIDIA, but like some vendor, and they basically tried to make it like an established like hardware accelerated physics. This was like marketed to gamers, I believe. I don't think it ever really took off, because eventually people realized actually CPUs are pretty good. CPUs are pretty decent, and especially with today's, where you have a bunch of cores, and you can just have a physics core, and at least in the like game setting, it just works pretty well. That being said, basically today, or like at least the way Motoko does it, it's just a single thread CPU processing. Okay. It's pretty fast, but I think you'd probably be hard pressed to distribute that specific architecture. Actually, probably some of the other, like basically if you had something like some of the game engine simulators are particle based. So for example, NVIDIA's Flex, and basically they don't represent bodies as like a rigid mesh. Yeah, it's literally just like a bunch of particles that have some like stickiness where they stick to each other applied. And I believe there have been some attempts at like distributing that, where basically you have like cells of the world, and every node basically computes all the particles that are like in this specific cell, and then they like hand it off to some other node. Okay. But we're not using that today.
Interesting. So we're talking about simulation, and tell me a little bit about the process for, the relationship between your training data and your simulator, and like how you load all that up, and like how you build the simulation. And, are there things that you've learned about integrating simulation into AI training pipeline that are maybe, not intuitive, or, maybe, simulators weren't really designed to do this, and so it was kind of hard, but we figured out how to do X, Y, Z?
Yeah. So I would say for the simulation, and this is actually kind of following the what we just talked about with the distributed aspect of it. One reason why we're not like pushing that super hard is because we actually can just horizontally scale it. So actually the way we basically do our training, which is basically running a lot of simulators. So you can distribute it in this way. It's just that the simulators are all independent of each other. Like they all simulate the same, like the whole scene, but they all have like different, like they all basically run like different, like they all run the same scene or some randomized version of it. But they basically instead of like serializing all the attempts, we just parallelize like 10 or actually more like 1,000 of them. So the way we actually run our training is we have like one box that actually does the like TensorFlow like computation for actually training the network and like taking in that data, and then we have a bunch of like worker or like evaluator machines that basically like take in the current best guess for the policy, which is like our trained neural network, and then they basically roll that out in a simulator, which basically just means they run it over and over again. And so this happens on like hundreds or thousands of machines like in parallel. But they don't really talk to each other. Like they just do this on their own, and then they actually send this experience back to the optimizer node, and that's basically where we crunch the numbers to actually improve the policy.
So you generate a policy, generate a network, you push it out to a bunch of different nodes in parallel. Like what's the input to those nodes? Are you giving each of those nodes specific input, or are they just kind of running things in random and computing a function or something like that across a random distribution?
Yeah, so the worker nodes, they basically receive the parameters for the policy, and there's like some shared configuration for like what's the kind of scene are we running, like what's the robot, and like where are the objects that we're interacting with, like what's their initial positions. There are actually a couple different ways of how to communicate the results back to this like central like mastermind machine. Mm-hmm. So one way is if you actually have the workers do the gradient computation. So they roll out the physics simulators, and then they figure out some kind of reward or cost function for this. And like, was this a good rollout? Like, did we end up in a good state where, like, for example, when you're moving these blocks around, like, did did the right block end up on top of the other right block? And then the workers figure out, okay, if my parameters were like tweaked slightly differently, I would have gotten a better outcome this time.
Yeah.
And then the other approach is to just send over the raw, like what happened in simulation to this optimizer machine, and then let the optimizer figure out what the parameters should be and like how we should change them.
Okay. And which do you tend to do? Do you do both, or?
Yeah. So right now we do the sending over the experience, or the latter thing, which is just because it's simpler for the most part, because then basically the workers are kind of dumb and they don't need to worry about that much. But there's a situation where this can actually be problematic, especially if your observations are big. For example, if your observation, which is like what your policy or your agent is using to make a decision for what to do next, that is something big, like an image from a simulated camera, then you don't want to send that over the network just because there are so many of them and just clogs up the entire bandwidth. That's where we'll probably look into switching to the sending over the gradients over the network over the next few months, especially as we move to these more like high dimensional observations.
And is the infrastructure that you're doing all this with, like, is this all handcrafted stuff? Or like I had a conversation with Ian Stoica about Ray the other day. Like, are you using something like Ray to do this?
So we're actually using Kubernetes. Yeah. So I believe we did like an infrastructure blog post about this a couple months back. But basically we run lots of Kubernetes clusters across all of the major clouds as well. Like we're running on Azure, we're running on AWS. Okay. We also have some stuff running on Google. So yeah, there's a lot of compute. The way you actually implement this using these tools is actually somewhat simple. You basically just tell Kubernetes, in our case, to here's this batch job, run this thing once for the GPU optimizer, and run this thing once for the couple hundred worker machines, and it just kind of goes and does it. But there is there is a ceiling there where you can't, just because this is not really the original use case for Kubernetes. I believe what they recommend as a limit is like not more than say 10,000 nodes, which is a lot, of course. Like
and have you bumped up against that limit?
So we have bumped against previous limits where the limit was something like 5,000, and then it won't crash, but it will just become like more and more unhappy and just stop responding, and like basically things will become weird in the cluster.
And how long are these simulation jobs? Are they, they're not like on the order of training jobs that are days and days. They're much shorter. Is that the case here?
Yeah. So basically, one specific cycle, this is much shorter. Like I believe like one specific cycle of basically get the current policy parameters, do a bunch of rollouts, send them back. That's something like maybe like a second. But the way we actually start them is we basically just keep these like rollout machines around in the same way that we keep the training. So they're just one like temporary cluster, basically.
Okay.
And that cluster will just stay around for the duration of the entire training, which is like maybe like a day or half a day.
Interesting. And so, all this is to help you develop a kind of a better model via simulation. Like, what do you do when you want to test that in the real world?
Yeah, this is the
really interesting part.
Yeah, exactly. So the kind of interesting thing is that a lot of other areas in machine learning, they just kind of stop short of that, and they're like, well, this is a model looks pretty reasonable,
right?
So it's fine, we're done here. And so we're actually really adamant about like jumping through all the hoops to actually make it run on the robot.
Okay.
Because we found that it helps like keep us honest, basically, and it's like. It's very easy to be impressed by like cool stuff happening in a simulator, but usually there's some caveats that make it harder. For example, like if like some of the like robot meshes like aren't actually like touching each other or something.
What's a robot mesh?
So basically that's kind of just the shape of like some like part of the robot, like a limb of the robot.
Okay.
And usually, for example, for when you're determining whether like the robot is pushing something, you do this like collision test of like, is the robot colliding with an object? And if yes, then you push the object away. But the thing is, like, while you have this super nice like visual rendition of the robot with like a nice like it models all the aspects in like screws or something. Yeah. Often the geometry is actually used for this collision check, which actually determines what's happening in the like physics wise, might be like a simpler version of this geometry. Like it might just be like a cylinder where the actual robot is something super complex, with rounded corners or something like that.
So your angles are all off, and kind of this error just compounds.
Yeah, exactly. And at the same time, like this can also like kind of like trick you into thinking that something works, whereas it wouldn't actually work if you tried it in the real world right now. And so the way we actually run our policies on the real world. We have developed a system called Robots as a Service, which basically means that the robot goes onto the network, and then people can connect to it and run specific algorithms or the models that they trained on the robot. And so there are some specific technical things that are just non-trivial, because it is a real-time environment, and you can't just basically it's much harder than just simulating a piece of software like people often do with Atari games, for example, for training. You have to be careful that you don't miss a cycle, because otherwise your policy will get super confused, because your time step will just be longer, for example. So basically, working on all these artifacts has actually turned this robots as a service system into a pretty big engineering project here.
So the example you gave struck me as something that is more of a training artifact and training issue, as opposed to deploying it to the physical robot. How does it manifest itself on the physical robot in such a way that you could do something about it there?
Mm-hmm. Yeah. So the specific example of so in simulation, you would start out at t = 0. Then you get some current state, you decide what you want to do, and you set the action. But basically, while you're thinking about this, the simulation is stopped, right? It's paused. So basically, you do this computation, then you get your output, and then you advance the simulation by one step, and then you repeat. You think again, and you step again. In the real world, of course, all of this happens simultaneously, and you don't get the chance to just pause and think for a while.
So you've got inertia and continuous variables and all this stuff that
exactly. But you raise a very interesting question there. Is it a training problem or an evaluation problem? Mm-hmm. And actually, for most of these things, it can be both. Sticking with the timing discrepancy example, there's basically always this is pretty much a decision we have to make for every issue similar to this that comes up. Is are we okay with investing time in actually ironing out this issue in our software stack, or should we just be oh well, I mean, if there's some fluctuation in the time step, then we can just train with that and basically just add that to the set of things that we randomize in simulation.
Right.
And basically, there's always a balance out of these two choices. Either make the simulation harder or make your real world system more predictable to execute. Mm-hmm. And so this is kind of an area where you have to pick your battles to some extent.
Right.
Because if you just have too many unknowns, then while there's it should be theoretically possible for you to be able to learn a model that can cope with all of these uncertainties. Yeah. It will just be very hard in practice to debug it and inspect it and see if something goes wrong, and you can't. And then you will see it break, and then you'll be well, so why did it break? And basically, getting to the bottom of that requires you to exactly do this part where you remove as many of the unknowns as possible. Mm. But you're totally right that basically in the end, our policies eventually we want them to be capable of. Basically, you put them on a new robot that is very terribly instrumented or has really weird software that causes lags and delays, and just figure it out. I don't think we're there quite yet.
Okay. And so you call this robot as a service. Is it on demand? You have a bank upstairs of thousands of robots just swinging around, or do you have, a robot or two connected to the network that folks can there's a calendar, an Outlook or whatever that they schedule their robot time with? How cloud-like is this?
I really wish it would be the former, but it is in fact closer to the latter. So we actually thought about, and actually some folks over at Google, I think this was Sergey Levin, they actually did this. They bought a bank of robots. They bought, I think, around 50 or something robot arms,
right,
and just had them do these grasping tasks over and over. We thought about doing that too, but at least with the current setup, it's exactly that. We have to fetch. We have a couple of other robot arms, and these are individually connected to the network. And we usually do the scheduling by whoever is around the robot at the time.
So scheduling by proximity.
Exactly.
Okay.
The main reason why we actually need a specific system for accessing the robots there is that. So these robots all come with software, right? They come with some kind of software. They come with either with some integration for ROS, which is the robot operating system, which is a big open source effort to provide a very unified framework for.
You're not up at ROSCON? That's going on now, I think.
Or is it going on right now?
In Vancouver.
Oh, yeah. Great. Well, shout out to ROSCON. So we're actually not using ROS.
Well, that explains it.
Yeah, so we found that ROS is actually really great if what you have is you have a robot and then you have a bunch of other things around it that you want you want to use. For example, you have your robot arm, and then you might have some a LiDAR,
right, they've got a bunch of modules
sensor. Yeah, exactly.
Very extensible.
It has so many, and you have tracking cameras, or you have maybe you have like one robot that is your arm and then one robot that is your gripper, and they need to be independently controlled or something like that. And we found that's really great that like all these things already ship with drivers for ROS, and you can just plug them together, and they will just work pretty much out of the box. I think for us it kind of comes back to the issue we talked about before this, where there are just timing uncertainties basically, and you don't really know what's going on inside the system. For example, if you had this case where you have a robot and you have some external sensor, and in ROS, they would just appear as like, here's a robot, here's a sensor, great, you're all set. But actually, there might be like subtle things there where, for example, the timing updates for both of these systems might be out of phase, where like the robot updates and then there's a delay and then the sensor updates, and then you will have like a timing lag there. And while this wouldn't matter in like for a lot of the like classical applications where you do something where like you collect data over 10 seconds or something, and you're basically doing this in a very slow way, and then you don't really care about what these like tiny differences. It causes problems for our case, where we try to instantly react to like if something changes in the environment. You might be like tens of milliseconds before we feed this back into the policy to like correct for that. And so this is why we actually have to be like super careful about like what are the exact timing phases of all these sensors. And so we found that a lot of the ROS abstractions are actually, they kind of encapsulate this and hide it from you, which is actually great, I think, for the majority of use cases. It just doesn't work that well for us, where we actually do need full control over these things.
Okay. So did you write your own operating system, or is it more like less like an operating system, more like a thin layer that, you know, I'm assuming that at the bottom of this, it's all kind of just you're controlling stepper motors and stuff like that through IO ports, and you know, there's got to be some kind of, you want some kind of software layer there to make that a little easier. Did you just roll that yourself?
Exactly. So it's pretty much like a layer of middleware, basically. So we didn't really write our own OS or something.
Right.
So for some of our robots, we basically get rid of all the software that they ship with. Yeah. And just basically like if there's some firmware on like some embedded microcontrollers on the robot, then we usually won't touch that, because that will also usually be fast and predictable, and like well defined.
Yeah. But so the issue with the off the shelf option was like code path lengths are, you know, variable because they're accounting for plugging in like external modules and all that kind of stuff. Is it that?
Well, yeah. So there's definitely a lot of complexity in that. Like they basically have this entire framework for being like plug and play. But like there are actually also like real operational issues where, like, for example, like the timing issue I just mentioned, like wouldn't be because they like, it's not that crazy basically that we have to like make sure that our code has like constant execution time or something. Yeah. It's just you have to like, for example, like usually these like systems have some kind of trigger signal.
Okay.
And you basically just have to lay your code out in a way that like, now my cycle starts, you trigger all the systems, basically you synchronize all of them, and then you like read out all the data, something like that. And that's how you synchronize all these things. So it's not so much like really like dark magic of like performance optimization. Okay. It's basically, for the most part, we just have like a very specific usage pattern that requires like carefully thinking about like basically when do we do what.
And so pulling this all together, you're trying to develop a technique that allows the robot to, you know, be more like the human and can kind of do, you know, fine-tune course correction, you know, as it's operating. And you train all these models in simulation. Like, how do you then use that with the robots and do the inference to make those course corrections? Like, how does all that part work?
Mm-hmm. Yeah. So basically, right now, what we're still like aiming for is that we actually don't do any fine tuning basically of our model in the real world. So we train our model in simulation, and then we basically just roll it out on the real robot. Like you gather all your sensor data like from the robot and from your like internal, from your external like cameras and tracking systems and stuff like that, and you feed that into the policy. You do the inference, and then you react to that. And so basically the adaptation loop for like figuring out like differences between the real world and the simulator right now is actually like, at least for us, it's pretty much manual still. So there are lots of ideas for basically doing this kind of like meta learning where you learn to adapt to a new environment. Right. And we've had some initial success with that for basically imitating a human doing some behavior. And then you would figure out, it's like, oh, what are the semantics that the human intended to achieve with this task? I think this is probably more like a general statement. This stuff is still pretty early, both in the robotics and the like ML communities. Yeah. But it is super interesting, and eventually we'll want to do something where like we have a bunch of the different simulators we talked about. Might even have like different kinds of robots, and basically just increasing the like breadth of this distribution, so you encapsulate like more and more things, and really hope that your policy gets to the bottom of like, I see, this is how I learned to like control a new robot in an entirely new environment.
Okay.
So this is something we're super excited about, and eventually we're hoping that like this will enable a robot that can truly solve a variety of like very complex tasks on a variety of different robot platforms.
Okay. And so if I wanted to learn more about this, dig into the details, like see it in action, like have you published code on this, or like, what would be required for someone to kind of, play with this and try to replicate what you did?
Yeah. So we did a pretty big release a couple months ago where we basically put some of the things we talked about together, like the domain randomization part and the part where you observe a human and figure out, okay, I want to do like this specific task, and like the robot imitates this in like a new setting. We have a release there where we basically show how it works, and like show how the networks are aligned, and like how they basically how we feed the data from one to the other and how they're trained.
Okay.
And we'll probably be publishing at least parts of this robots as a service layer that I just talked about, together with like our next set of research results there. Like we figured it doesn't really make sense for them to just be like kind of on their own, because then
there's a lot of moving parts, right?
Exactly. Yeah. And so the issue there is that like even if you open source the code, then it's like, well, great, you can get started today. Just add a really expensive robot to the mix. But like we'll definitely be, as we publish our research, we want to release like both the research and the infrastructure parts required for it.
Okay, cool, awesome. Well, Jonas, thanks so much for taking the time to chat with me about this. It's really cool stuff.
Awesome. Thank you for having me.
For sure.
All right, everyone, that's our show for today. Thanks so much for listening and for your continued feedback and support. For more information on Jonass or any of the topics covered in this episode, head on over to twimlai.com/talk/76. To follow along with our OpenAI series, visit twimlai.com/OpenAI. Of course, you can send along your feedback or questions via Twitter to @twimlai or @SamCharrington, or leave a comment right on the show notes page. Thanks once again to NVIDIA for their support of this series. To learn more about what they're doing at NIPS, visit twimlai.com/NVIDIA. And of course, thanks once again to you for listening, and catch you next time.